Dear all, I'm now demoing on the tutorial 1. Okay, we are actually having the class on the tutorial 1. So, starting from question 1, okay, the coin is tossed 3 times. So, it's a coin. It didn't mention anything about it's a fair coin or not, so in general, we'll consider it as a fair coin. In general, a fair coin is supposed to have head or tail as your outcome. Okay, so it's tossed 3 times, so you know that it's actually having 3 continuous outcome. All right, and then what's the probability? Okay, so when you're actually identifying probability, then you know that you need to have event divided by sample space. Okay, so they lands on exactly 1 time. Exactly 1 time. All right, so how are you able to actually identify this so-called exactly 1 time? So head and tail 3 times, event divided by sample space exactly 1 time. So these are the information that you have right now. Okay, and you're expecting a probability. So the first thing you know that is your range is definitely between, your answer is definitely between 0 to 1. All right. So from here, exactly 1 time. Maybe we start with identifying the sample space first. Sample space on coin toss is tossed 3 times. What are the all possible outcomes that we have? If we still recall, we can have 3 things right over here, and then we can have HT or HT or HT, for example. So this one I consider is H, this one is considered as T, head and tail. So in that case, you have this. How are you able to actually tell what are the all possible outcomes? Is this independent? Is the order important? Remember your permutation with combinations? Because why? Every single action that you have over here at your first coin toss doesn't really affect your outcome of the second coin toss. Every time when you toss you toss a coin, the next coin can still have the head and tail. The third coin can still have the head and tail. So it's actually independent. And then when you are actually having the independent. When it's independent means it's with repetition, and is order important? Is order important over here? Do you think so? Because when your order is actually different, you're actually having a different kinds of outcome over here. Okay, so in that case, order is important, and also what repetition is correct. So in that case, you can actually apply the first formula. If you still recall NR, then your N is actually what? 2. Your R is actually 3. Because you have 2 possible outcomes, and then you actually toss 3 times. So your total possible outcome is actually 8. Of course, if you want to double check your answer, then you actually can write down all the possible outcomes that we have. We can have, for example, your first coin toss is T and then H. For every single first coin toss, you can have potential outcome another T and H, right? So it can be T, H, or T, H, H, T. Alright? This makes sense to you? And then the last one, if you toss the third one, is it possible for you to have another set of outcome? Yes. So in that case, TH, TH, right? And then T, H, H, T. And you can actually put T, 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 H, 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 H. These are all the different possible outcomes that you can actually have. It's something like a binary table if you learned it before. Okay, but yeah, you can actually think about how you are able to actually do this in a so-called raw way or in a formula method. Okay, so in that case, we are done with the sample space. Sample space, we are done. And how about the event itself? Exactly 1 time. So in that case, how are we able to identify exactly 1 time? Wait, yeah. Okay. So considering this kind of situation, you can have like H. You see exactly 1 time. Yeah? Whenever you've identified the first one as H, the rest of it you can't have H anymore. And also the rest of it must be T, must be T. So in that case, you don't really have other choice but only one. Go for a second situation. If your H is actually middle, the next two must be T as well, right? Because you don't have other choices but putting it T, because you have a hard rule that exactly 1 time. So another third scenario. So you actually have the H at the last. Again, same thing. There are only possible T over here. You don't really can put another H over here because you violate the rules. So in that case, this one is only one choice, this one is only one choice, this one is only one choice. When you plus it together, you get 3. Okay? Basically all these are one choose one, one permutate one, one permutate one, one permutate one. It's the same. So in the end of the day, you're getting 3, and your probability is supposed to be 3 over 8 in this case. Okay, because you're getting event divided by sample space. What's your event? Probability of x equals to 3 over 8 x land on heads exactly 1 time. I know that this one can be like, oh, you feel that the question is actually very simple. You can do it within seconds and so on. You don't really need all this kind of derivation and so on. But if your problem is getting a bit more complicated, okay, this will still help you to get all the answer for those complicated questions. Maybe you try yourself, you try to change this question, a coin, maybe to a dice. All right, and then you try to find out that what's the probability that, and maybe give you an example questions. What's the probability for 3 rows of dice? Yeah, 3 rows of dice, and then every time the outcome of the dice is actually different. Every time the outcome of the dice is actually different. What's the probability for every time the dice is actually different? Okay, try to think about it. If you are having your answer by yourself, then it's good to hear that. But if you are not, then you probably might want to think in a more in-depth manner. How are you able to solve it using the example over here? Okay, what I can give you a hint is, think about the sample space of 3 rows of dice. When is the dice is actually independent or independent? Sorry, dependence or independent? Are you able to use the permutation with combination, or you are actually supposed to use permutation? Permutation with repetition or permutation without repetition? When to use which one? Okay, so these are the hint I can give you. So please try it out. If it's 3 dice, probability to get all 3 dice to have different numbers. Okay, think about it. Okay, then you can try on this one over here. Then an urn contains 6 red marbles and 4 black marbles. So you know that under urn you actually have the urn. You have 6 red. If you're considering this one is actually cross, black is actually circle. 6 red, 4 circles. All right. So 2 marbles are drawn with replacement. So you know that you only draw 2 times. Okay. And you know that it's actually with replacement. If you still recall in the class, with replacement means that every time you take it out once, you put it back. So your whole environment over here doesn't change. No change. So in that case, what is the probability that both of the marbles are actually black? Black, yeah? Both of the marbles is actually black. 2 things happen together, you use a multiplication rule, right? So for you to get your first marble to be red, how do you get your first marble to be red? Wait. 6 red marbles. Black marbles. First marble to be black. Sorry. How do you get the first marble to be black? When you're considering this one, sample space is 10. First marble is actually, the probability for you to get marble is actually 4 events. Okay, remember that. The events is whether you are able to get the black or not. This is your first pick. In your second pick, does here change? It doesn't change because once you take it out, you put it back again. So in that case, another 4 over 10, right? Because both of it is actually black. So in that case, your answer is actually quite straightforward. Or you want to put it 0.16, it's so fine. All right. But again, if I were you, I would actually think about, okay, how these questions can be expanded. For example, what's the probability that both of the marbles are red? What's the probability that one red or one black? What's the outcome is without replacement? If I draw more marbles, what will happen? Okay, so try to think about so-called extended version of the questions. Okay, because these questions are designed actually for your basic understanding, and you can actually always think further. All right, then you have question 3. Okay, a card is drawn randomly from a deck of ordinary playing cards. So you're supposed to know that the playing cards, there are 52 cards in the deck. There are 13 spades. There are 4 aces as given in the questions. Okay, you win RM10 if the card is actually a spade or an ace. It's giving you a winning condition. Okay, and what is the probability that you will win the game? When you are trying to link these two, win and win, so you know that the event that you actually want to measure is actually spade or an ace. Okay, spade or an ace. So within these 52 cards, you have 13 spades, 14 ace. 52 over here, eventually is telling you that this is a sample space. All right, and for you to have 13 spades, 4 ace over here, then you roughly know that there are 2 different kind of categories which can be intersected together. And there's one more extra thing here is what is one ace that is also a spade. So if we try to lay down the information over here, sample space equals to 52. Probability for you to get a spade, okay, as spade, A, aces. Yeah? Of course, you can put it in a more complete manner. I'm just have a fast writing, so we're having this one. Probably a spade is events. What is your events? Probability for you to getting a spade. You have 13 out of 52, right? That's why you are getting this probability. Probability for you to get an ace. Out of your sample space, there's 4. There's actually ace. There's one ace that is also a spade. Probability of S and A happen together, which is 1 over 52. And right now you are trying to calculate probability of ace, a spade, or an ace. This one is N, okay? This one is N. This one is OR. So when N is actually using an intersection, so OR is actually using a union. You don't really measure it happens together. When it only happen spade or ace, you still consider it as well. So if you still recall, the probability is supposed to expand this way. Because it's dependence, because you're actually having this kind of intersection session, so there's a dependency over here, so into minus. Sorry, there is actually not mutual exclusive. Not about dependency, it's about mutual exclusive or not. So S A. So in that case, you will get what? 13 divided by 52 plus 4 divided by 52 minus 1 divided by 52. So you have 16 divided by 52. All right. Or if you want to put in the decimal place, your choice. But it's gonna be how much? Let me see. Oh, okay. Or you want to simplify for 13, or you see 4 divided by 13. You can put 0.3077 is also fine. Okay, your choice. Okay. So from a group of 8 professors and 9 students, an admission of committee consists of 5 professors and 3 students to be formed. How many different committees are possible? Again, this one is actually trying to find out a permutation, outcome of a permutation or a combination. Order is important over here. What do you think? Is order important? When the order is not actually important, because you don't really need to know that, oh, Professor 1 is actually picked, and then followed by Professor 3, and then followed by Professor 5. Okay, it's different from this one. It's actually different from cases that you actually have in here. Okay, first toss and second toss and third toss actually give you different kind of meaning over here. So that's why over here, you just need to use a choose a combination outcome. And you know that for 8 professor, you are actually choosing 5 among of it. And for 9 students, you're choosing 3. So basically your calculation is 8 choose 5 times 9 choose 3. Or some of you might write in this way, 8 5 times 9 3. Okay, still giving you the same answer. Okay, but as long as you still recall that it's actually following the formula that we have in the class, combination without repetition, because your professor not supposed to pick 2 poles in general. Okay, of course you might argue that, oh, it's actually not mentioned in the question, so the professor can hold 2 poles and so on. But if you are really delivering that kind of answer, then you need to put in those argument inside as well. Or else, in general, when you're selecting a committee, I mean, once one professor is selected, you can't select another professor. I mean, you can't select another post with the same professor usually. And actually, the question specifically mentioned that from 8 professors, you choose 5. Okay, so you kind of can't argue on this particular point somehow. So in that case, this result is actually 8 choose 5 is 8 factorial. If I recall, is 5 factorial 3 factorial times 9 factorial, then 3 factorial, 6 factorial, right? So in that case, it will become what? So this one you can, and this one you can actually cancel off. You have 8 times 7 times 6, and then this one is still here, 3 times 2 times 1 plus times this one, and this one you can cancel off, just like 9 times 8 times 7, and then you have 3 times 2 times 1 again. So how much? So you can cancel off this one and this one, you can 56 times this one you can cancel off with 3, this one you can cancel with 4, so 3 times 4 12, 84, and you will get how much? 4704. Okay, this one of course calculator. So basically this is your answer. Alright, this is another way for you to actually use the combination outcome. Okay, so this one is a much more lengthier questions. Okay, the table below shows the number of students who prefer an ice cream topping. So you have 2 sets of information. One set is actually toppings over here. Another set is actually a number of students with different academic years. So you actually have all this information over here. Okay, so what's the probability that a student prefer chocolate toppings? Probability that student prefer chocolate topping, you only need to know about probability of C. Remember your marginal probabilities. Regardless of the other information, you only focus on one, which is probability of chocolate toppings. So in that case, you are actually doing probability of C equals to probability of C first year plus probability of C second year plus probability of C third year plus probability of C fourth year. So in that case, it's how much? 14 plus 11 plus 28 plus 19. No, because this is a probability, right? So you need to divide by your total sample space. What is the sample space? So you need to do some calculations. I have done some calculation over here, so I can just write down. The summation over here is 72. Over the columns, this one is 66, this one is 66. This one is 47, 44, 61, 52. Okay, all these are sum. Huh? This one is also sum. And then in total up is actually 204. So you actually have a total number of students of 204 over here. So all this is actually divided by 204, divided by 204, divided by 204, and divided by 204. Alright? Then equals to how much? So from here, when you do your summation, because all of your denominator is the same, so you will actually get 72 divided by 204. Alright? Okay, so probability of CC basically is chocolate. I'm still gonna write it down because why? I really want to train you all to make sure that you explain what you are actually writing. Like, okay, what is PC? What is C? C is actually referring to chocolate. Okay, and then what is first? First is actually referring to first year. So you just write your first is actually first year. Don't assume that the examiner or marker knows that what you're referring to. Okay, even the marker knows, they will assume that they don't know, because why they supposed to like helping you in this sense? All right, you're supposed to explain all your formulas over here. Okay, so this one is the marginal probabilities for preferring chocolate toppings. What is the probability that the student is in third year and prefer beans? Is in third year and prefer beans, okay? And yeah, so is you are calculating in terms of intersection. Probability of third year intersect beans equals to probability of third year, okay? Intersect, third year is over here, intersect with beans. So it's actually 22 of your event, and then divide by sample space, 204, okay? How about third one? What's the probability that the student is in third year or prefer beans? Probability for you to be in third year and prefer beans. Probability of third year. Union beans. If you want to apply formula, then you can actually apply probability of third plus probability of B minus probability of third intersect with B. So in that case, you can actually apply this one. Scroll too much down. Okay, so let me see. Third is this one, so you're actually picking up this one. So it's 61 divided by 204 minus PLB. Probability of B. Probability of beans is this one. 66. 61 over here, 66 over here. So it's 66, 204 minus probability of third intersect B. So it's actually coming from here. So you minus 22, 204. And in the end of the day, your answer is actually 61 plus 66 minus 22, and which is, okay, 105 divided by 204. All right. Of course, if you want to sum one by one, it's also possible, because what you are considering is actually this part. Okay, then you can just sum 1, 1, 1, 1, 1, 1, and you still get the same answer, 105. How about question 4? What's the probability that the students, okay, I cannot resize it. Never mind. What's the probability that the student is in or first year? Is in first or third year? First or third year? Probability for you to get first year or third year. So this one, do you think they are dependent or independent? When they are having, do you think they are mutually exclusive or not mutually exclusive? You have first year over here, you have third year over here. Do you think they have any intersections? They have no intersections at all. So in that case, you can just sum the outcome together, and then you without minusing any of the intersection part, because for this for question 3 cases, they have intersection, means that they are not mutually exclusive. But in your question 4, it's actually mutually exclusive, because you don't have any intersection at all on the data that you have. So in that case, it can safely become probability of first plus probability of third equals to how much? 47, 204 plus 61, 204, and you get the answer of 108, 204. That is for question 4. How about question 5? What is the probability that the student prefers jelly topping? Okay, given that the student is in 4th year. Okay, probability of prefers jelly topping. So you're actually measuring this information, prefers jelly topping. So jelly topping. But given that the student is actually in 4th year, Okay, so if you want to measure probability of a light jelly topping, it's actually this whole thing, right? Okay, this whole thing, jelly out to here. Okay, but right now, given that you have already know that the focus that you actually put it in is actually 4 years. So what is actually the outcome of your result? We are not talking about intersection over here. You are not talking about the probability of jelly and 4th year happen together. We are talking about you have already know that the evidence where the one that you're actually investigating is 4th year. You're only considering this part right now, okay? Without considering the first, second, and third anymore. So in that case, that's the reason why you are supposed to be expanding this one to be probability of J intersect 4th year divide by probability of 4th year. Okay, so from here, probability of J intersect with 4th year is how much? It's actually 14, all right? 14 divided by 204. And then you have a big one. Probability of 4th is how much? If you go back and check it, so let me see. So it's actually 52 over 204 as well. Because again, 204 is actually a sample space, right? 52 divided by 204. And you cancel off these two, and you actually get 14 divided by 52. All right? So this is your probability outcome for conditional probability. Same goes to the question number 6. Probability of second year, given that the student preferred beans topping. Probability of second year, given that it's actually preferring beans topping. So equals to how much? Probability of probability of second year intersect with beans divided by probability of beans. So from here, probability of second intersect with beans is, if you refer back to the table, because I'm lazy to scroll it back because I have another screen over here, second or intersection with beans is 14, okay? Divided by 204. Oh, my iPad is lagging now. Maybe it's overheating. Okay, and then probability of beans is 66 divided by 204. So in the end of the day, what's the final outcome? This one cancel off, this one cancel off. 14 divided by 66. Okay, so that's all for the tutorial recording. If you have any questions, please send your problems to me via the Microsoft Team chat. Okay, thank you very much.